Hello everyone. In today's class, we're going to talk about power function and polynomial function. Okay, so now what is power function? So by definition, a power function is a function that can be represented in the form of fx equals to x to the p power, where the base is the variable and the exponent p is a number. So what is the most common power function you've seen? Think about that. Yes, it's going to be a quadratic function, right? Because the base is the variable x, and then the exponent is a number. What others? You may think about that. Yes, the cubic function, also a power function. If you think about that, fx equals to square root of x, also a power function, because square root we can interpret it as 1/2 of x. Even our identity function fx equals to x also is our power function because the exponent equals to 1. All right, so now if you think about, I'm going to show you a map. What does y equals to x squared, y equals to s to the 4th, y equals to s to the 6th, and then y equals to x to 12 look like? Now, if you take a look at our decimal, y equals to x squared look like a parabola. You know that. What about s to the 4th? Also parabola, but it's narrower because the increasing rate is faster, right? Because think about when x equals to 2, y is equal to 2 to the 4th power, which is 14, whereas for the red one, if x equals to 2, x squared equals to 4, which means y equals to s to the 4th grows faster. So now let's take a look at s to the 10th power. Still a parabola. So you may already find some pattern here. So if the number is an even number, the function is going to look like a parabola, right? So now similar question. Make a guess. If the power function, the exponent, is an odd number, such as 3, 7, 9, or x to the 14, these are odd number, what do you think they look like? They're probably similar to the cubic function, which is like this way, right? So now let's check it out. Okay. So now let's take a look. Y equals to s to the cube. We know that it's the cubic function graph. Now we find another odd number exponent, which is 7. Also look like cubic function. Y equals to x to the 31. Still, the red line is just a cubic function. What about y equals to x to the 15th? Again, another similar graph about the cubic function. Isn't that amazing? So here is the long run behavior of a function. First of all, we need to know what is a long run behavior. So a long run behavior means the behavior of the graph of a function as the input takes on large negative value which means as x goes to the negative infinity and takes to the large positive value, which means as x goes to the positive infinity, it referred as the long run behavior of the function. So here is the definition. So I'm going to show you what does that mean. So in some textbook, they may call this is the end behavior, which means what does the end look like? Straightforward. So now take a look. As x goes to infinity, so x has two directions, either positive infinity to the right or negative infinity to the left, right? So if x gets bigger and bigger, the graph goes up, right? So this is the end behavior. And also, as x goes to negative infinity, y goes down. This is another end behavior. Okay, so now let's take a look at the even functions. So as x goes to infinity, positive infinity, which means goes to the right, the graph goes up. So that means the end behavior on the positive infinity is going up. Similarly, as x goes to negative infinity, y also goes up. So that's also an end or long run behavior. As you can see, all the odd function or even function, they have a similar end behavior. For the odd function, the end behavior is going to be similar to y equals to s to the cube, which means as x goes to positive infinity, goes to the right, y goes up, which is positive infinity. And then as x goes to the left, which is negative infinity, y goes down, which is negative infinity. All right, so now let's take a look at the even functions. The power function with an even exponent. Well, you might notice that as x goes to the right, y goes up, which means a positive infinity. And then as x goes to negative infinity, the graph also going up. So that is also a positive infinity. So that's the end behavior or long run behavior. We just need to look at the end. What does the function look like? Okay, so here's an example. I want you to describe the long run behavior of fx equals to negative s to the 8th power. What does this look like? Well, you need to first of all think about what does the graph look like. Okay, I know that, hey, this is a power function with an even power, right? Even exponent. So that means the behavior is going to be similar to y equals to x squared. Okay, so the first step is this is going to look like this one, y equals to s to the 8th power. But there is a negative in here. So that means you're going to do some transformation of this function. If you take negative of the whole function instead of x, the function is going to have a vertical reflection. So that means the function is going to look like this one. Okay, so that's the graph of our function. Well, what would be the end behavior? Well, now we can say by the graph, we can say as s goes to the right, y goes down, which is negative infinity. As x goes to the left, y also goes down, which is also negative infinity. So this part is the end behavior for this function. Okay, now your time, try this one. Y equals to negative s to the 7th power. What does this look like? Okay, so I know that, hey, this function is going to be similar to y equals to s to the cube because they are power function with an odd power. So the function is going to look like this one, y equals to s to the 7th. Again, you take a negative. That means there is some reflection transformation for the function. So that means the function look like this one after you take the negative sign. Okay, so now what does the function's behavior look like? Well, as x goes to negative infinity, y goes up, right, which is positive infinity. And then as x goes to positive infinity, y goes down, which is negative infinity. So that's the end behavior, a long run behavior of the function. We don't care about what happened in between. In between, if you really want, you care, then we are in a short-term behavior. But before then, I would like to talk about some terminology of polynomial. So what is a polynomial? A polynomial function is look like a function can be written as fx equals to a plus in this form. It was combined by multiple power function because all of these is just power function, right? Okay, so for example, this is going to be a polynomial. This is a polynomial. And here is another example of a polynomial. A polynomial. All of this was made out of power function. This is one power function. This is another power function. This is another power function. This is power function. This is also power function. So in a polynomial, this is called terms. So that means in g of x, there are totally 5 terms. 1, 2, 3, 4, 5. So now let's look back to our fx function. How many terms are there? 1, 2, 3. So they totally have 3 terms. And then when it comes to terms, something that is very important that you have to include a sign. For example, for the fx function, the first term is a positive term, the second term is positive, the third term is negative. Why this is important? Because if you remember the power function example that we talked about, if you have a negative term, your function is going to turn upside down. Will have a vertical reflection because of the term. Okay, so now the next concept is degree. What is a degree of a polynomial? Well, a degree of polynomial is the highest power of the variable that occurs in the polynomial. I'm going to use this as a short writing of the polynomial. Okay, so in our previous example, like fx, what's the highest power in our fx function? It's going to be 4, right? So that means the degree of fx function is 4 because the highest power is 4. And now let's look at g of x function. So what's the degree of the g of x function? So now we need to look for the highest power. We have 5, we have 3, and 2, and another 5. So that means the highest power is going to be 5. So it means the degree of g of x function is 5. Okay, and then another concept is leading term. So a leading term of a polynomial means the term containing the highest power of the variable. So that also means the term with the highest degree. So for the fx function, our leading term is going to be 4x to the 4th. And then for g of x function, well, you have two terms with the highest variable, with highest degree. One is negative 2/3, the other one is negative 2x. So which one is the leading term? You only allowed to have one leading term. Well, if you think about that, maybe we can combine these two together since the power function have the same degree. So we have negative 2/3 minus 2, which is equals to negative 8/3 x to the 5th. So that means the leading term for g of x function is negative 8/5 to x to the 5th power. Okay, and then the last one is a leading coefficient. So I'm going to use a blue pen. A leading coefficient is the coefficient of the leading term. Okay, so now take a look. We know our leading term. So for the first one, leading term is 4s to the 4th. So the leading coefficient should be 4. For g of x, the leading term is negative 8/3 x to the 5th. So the leading coefficient is going to be negative 8/3. Okay. So now take a look at this example. h of p equals to 6p minus p to the cube minus 2. I want you to tell me how many terms are there. 3. So very good. So the function h of p contains 3 terms. Okay, so what is the degree of the function? Well, when it comes to degree, we need to find the highest one. This one is 1. It didn't say anything, that means 1. This one is 3. So that means the degree of HP function is 3. And what is the leading term? Well, the leading term is the term that contains the highest power. So in this case, it's going to be negative p to the 3rd. And then which one is going to be the leading coefficient? Well, the coefficient should be the coefficient that in the leading term. In this case, is negative 1. Okay. For a polynomial, for any polynomial, I should say any, for any polynomial, the long-run behavior of the polynomial will match the long-run behavior of the leading term. Okay, so now let's use the HP example. So I know that our leading term is negative p to the cube. What does this function look like? When we learned about power function, I know that, hey, this is going to look like a cubic function with a vertical reflection. So that means the function is going to look like this one. So the end behavior for this leading coefficient, negative p to the cube, is going to look like as x goes to negative infinity, y goes to positive infinity. And then as s goes to the right, which is a positive infinity, y goes down, which is negative infinity. So this is the long run behavior for negative p to the cube. But this long run behavior also matching the long run behavior of this polynomial, h of p. So that means h of p's long run behavior is going to look like exactly the same. As s goes to negative infinity, y goes to positive infinity. As s goes to positive infinity, y goes to negative infinity. Okay. So now let's try this one. So example, y equals to 0.2, x minus 2, s plus 1, and s minus 5. I want you to find a leading coefficient and the leading term and the degree of the polynomial, also the long run behavior. Of the polynomial. Okay, so how do we do this? Well, you might need to use your algebra skill. So the leading term for these would be what? If you think about how do you expand this function, that means you need to do the FOIL with all of these parentheses, right? But however, if you think about how does FOIL works, the FOIL works means what? You always multiply with the x, right? When you multiply the x, then you will get you to the highest leading coefficient and the leading term. So that means in this case, the leading term should be 0.2 s to the cube. If it's still confused, think about y equals to x plus 2 and s minus 3. This is FOIL, and after you FOIL, you will have x squared minus x minus 6, right? So the leading term is x squared. Why is that? Because you will have 2x multiplied together, that gives you the most x. So when we're considering the leading term, we don't care about what happened in between. So that means we don't care about what happened for negative x and minus 6, the non-leading term. So that means we don't need to worry about that when x is multiplied a constant. So what we care about is when x multiplied how many x, how many variable. That gives you most of the s, which gives you the highest power. And then why 0.2 matters? Because 0.2 multiply the whole function. That means when you FOIL these three parentheses, you have to end up for multiply 0.2 for everyone. So that means we need to consider 0.2 as well. Okay, so now after we found the leading term, it's not hard for us to find the leading coefficient, right? It's going to be the coefficient of the leading term. So the leading coefficient is going to be 0.2. So what about the degree of y, the polynomial? Well, the degree is going to equals to the highest power, which in this case is the leading power, which is 3. Okay, what's the long run behavior? Well, long run behavior is going to match in the leading term. So our leading term is 0.2 s to the cube. So this is going to look like a cubic function, but when you multiply 0.2, it's just going to compress the function vertically, so it doesn't matter. The end behavior is what we care about. How fast they grow, how steep the slope is, we don't care. So that means the long run behavior is going to look like this graph, and when we look at these two ends, we know that as x goes to negative infinity, y also goes to negative infinity. And then as x goes to positive infinity, y goes to positive infinity. So that would be the long run behavior. And now the last part is the short run behavior of a function. So a short run behavior is determined by the intercept and the turning point. Those are described as a short run behavior. So intercept, we will have a vertical intercept and a horizontal intercept. Now, let's use back to this example. Y equals to 0.2 x minus 2 times x plus 1 times x minus 5. Okay, so what's the vertical intercept? So vertical intercept also is y-intercept. Also, we call it y-intercept, sorry. Y-intercept or vertical intercept. That means when x equals to 0, the value of the function is the vertical intercept. So in this case, we substitute x equals to 0 into the function. I will got 0.2 times 0 minus 2, and then 0 plus 1, and then 0 minus 5. So that gives you 10, positive 10, and then times 0.2, which is 2. So that means your vertical intercept is going to be 0 and 2. Remember, an intercept of a graph is a point. So that means you need to write it into a point coordinate. Okay, so after a vertical intercept, we also need to talk about horizontal intercept, which is x-intercept. So as you can see in this graph, you can have more than one x-intercept. That's okay. Not like vertical intercept. You always allowed to have one vertical intercept, because by the definition of a function, remember our vertical line test? That means the line has to pass the graph with only one intercept point with the graph. Okay. So horizontal intercept is when y equals to 0. So look at our function. When y equals to 0, I have a 0 equals to 0.2 x minus 2, x plus 1, and then x minus 5 equals to 0. So we need to solve for 0. If this equals to 0, that means either x minus 2 equals to 0, because we know that 0 multiply everything equals to 0. In that case, the function will equal to 0. Or the second parenthesis, x plus 1 equals to 0. Or x minus 5 equals to 0. So that means we have x equals to 2, x equals to negative 1, and x equals to 5. So that means this is going to have 3 horizontal intercept with 2, 0, negative 1, 0, and 5, 0. All right, so here is the horizontal intercept. And that's it for today's classes. And next time we will talk more about how the quadratic function and other polynomial function. I'll see you next time.